And thank you for the organizers for giving me 20 minutes here to talk about what we're doing at Atom Computing. Thanks everyone for leaving the coffee room again and joining us here in the afternoon. So my name is Remy Notermans. I'm a strategic planning manager at Atom Computing, so I'm working at the product team, but by training I'm a physicist, and I actually started in the engineering team at Atom Computing. So a little bit of history of Atom Computing. The company was founded in early 2018. I actually joined not long thereafter, so my interviews were like in a coffee shop. We didn't have an office yet. And then at this point, we have over 60 employees. And we have an office both in Berkeley, California, the original HQ, and we expanded into Boulder, Colorado, with a 17,000 square feet facility where we can really build multiple machines. So what do we actually do? Well, we build quantum computers based on atomic arrays of neutral atoms. And we believe that's a very highly scalable approach. So we have a 100-qubit prototype in Berkeley, in California, and we're building the next-gen commercial systems in Boulder, in Colorado. And we hope to, we will offer these computers as a cloud-based quantum computing as a service, but we're also exploring options into like system sales, so like on-premise installation of these systems. So why are we building quantum computers? I think this sort of slide has been covered a lot today already, so I'll sort of skip over it, but I just want to briefly mention that quantum computing in one way or another is going to affect many, many different segments of industries. And either it's going to be a major accelerator or it's going to be a minor component just helping certain things move forward. It's going to touch all of our lives at some point in the near future. And so we're very excited to be a part of that. So what is our mission as a company? It's to build large-scale, fault-tolerant, universal gate-based quantum computers. Those are a lot of boxes that we need to check off, but we're very confident in our roadmap and like how we're making progress on all of these parts. And we do that by essentially focusing a lot on the hardware development. So I want to explain a little bit about what it means to have neutral atoms as your qubits. So we have this schematic drawing of a vacuum chamber that in real life is about this big, just like a softball. And then we actually hold our atoms in the vacuum chamber using a laser tweezer. A laser tweezer is nothing else than a focused laser beam. And exactly in the focus of the focal point of the laser beam, an atom wants to stay trapped, so you can sort of like trap it in that position and just drag it around by moving the laser beam around. So if you have an atom like this, you can turn it into your qubit by designating two of its energy levels as the qubit states, and then with a different laser, we can shine light on it and give it some arbitrary single qubit rotation. So we can do that also with 2 qubits, and we get into the quantum entanglement part of our system, where you put 2 qubits and 2 tweezers next to each other, and you shine a laser beam that covers both of them. And if you do that in a certain way where they interact with each other, you can create entanglement between the two. And in this like very high level way, you've created single qubit and 2 qubit gates, and now you can build your quantum computer. Of course, we have a few more qubits actually in our array of tweezers. So in this case, for instance, like a 10 by 10 grid, so you have your 100 qubits, but you should imagine that each qubit is being held by like a tiny optical tweezer. And you can scale this in 2 dimensions to many more qubits. But just to keep sort of the scale of this problem in mind, even if you make a big array like that, in the actual chamber, it's only like the size of the width of a hair. So it's tiny. If you illuminate all of those qubits, though, you can actually see them with your bare eyes if the room is dark enough. So that's pretty cool. But that's a lot of qubits in a tiny, tiny amount of volume, and we're able to do that because they are neutral. They don't have any charge, so they're not pushing each other around a lot. And that means that you can put a lot of qubits in a tiny, tiny volume. So sort of to give you an idea of like where this all fits, so we have that vacuum chamber, and it's a small part of the system that resides on an optical table. Sort of all of these like grayscale colored boxes that are in the center level there, they all contain optical systems. We use those to manipulate the qubits in any way possible, so either by keeping them in place, moving them around, doing the single qubit gate addressing, or doing 2 qubit gate addressing and the readout. And then we have a person standing next to it for scale. So what does that roadmap actually look like? So in a prototype system, we have 100 qubits, which is like the bottom left system. And right now, we're just pursuing the path of aggressive 2D scaling. So we're just making the grid larger and larger, which sort of has the quadratic scaling advantages. But in the future, we're going to scale into a 3-dimensional array and sort of make a cubic configuration of our qubits. And the amazing thing about this is it's going to fit in like roughly the same size vacuum chamber. So even though we're going up many more orders of magnitude with our qubit count, it's going to stay within the same footprint, if not smaller, as we move forward with like miniaturizing our optical components. So it's a very exciting way of like going from 100 qubits to the number of qubits that you need to achieve like the fault-tolerant regime. As you scale these qubits, you preferably also have all of your other qubit performance parameters to be compatible with that. One of them is the coherence times that we have. So our particular qubits, because they're neutral atoms, we actually use the nuclear spin of the atom itself as the sort of the qubit states of the system. And so we call them nuclear spin qubits. And the important thing to sort of take away from that is because it's the nucleus of the atom, it's shielded by all of these electrons, and it's actually pretty insensitive to noise in the way that we use it. And so because of that, we actually have these like pretty amazing coherence times of tens of seconds between the qubit states that we sort of get for free because that's just nature doing its work. But those tens of seconds provide really a lot of overhead to consider any kind of error correction, hybrid computing, running any deep circuits with many thousands, tens of thousands of gates. And we get that for free because it's nature giving us these atoms. So together with like the many, many atoms that we have, you can have enough computational overhead where you don't have to squeeze like the optimal performance out of the GPUs and the CPUs that you need to, for instance, calculate how your error correction works. So that's sort of the natural advantages of neutral atoms. They're all identical. We get these like long coherence times. We address them wirelessly, so you can address them in like a very tight volume of space. They're exponentially scalable with the laser array size, especially once we go to 3 dimensions. And as I mentioned earlier, we can get like millions of qubits in like pretty much the volume of a grain of sand. So that's pretty amazing. And this is not too much cutting-edge technology. I think the big challenge is putting a lot of components together into a single system. But the scientific fundamentals have been proven over the last few decades of research, as has been mentioned before, but like laser cooling and trapping, precision spectroscopy, manipulation of quantum systems, optical tweezers, and of course this morning, Professor Alain Spand and this entanglement experiments, all Nobel Prize winning research that at this point has come to fruition, and like pretty much it's just usable technology for the most part. Doesn't mean that we can improve a lot of things, but for instance, talking about laser cooling and atom trapping, which was groundbreaking in the 90s, right now you just set it up and it works, and that's pretty amazing. It's no longer an R&D component for us. It's just something that you design, you assemble it, and it works. So that's a very strong foundation in sort of pursuing this kind of technology. So where are we at now as a company? We built the prototype system. It's a 100-qubit machine that's in Berkeley, California. And as I mentioned before, we're now scaling this technology to improve the performance, the quality, also the reliability for commercial deployment if we want to go to quantum computing as a service, and also for system sales. And this next generation stuff it's all being done in Colorado. We also make our custom control systems. So I now realize this morning that this box is way too low. But we have our own proprietary hardware and firmware for all of our control systems. So we very quickly realized that all of the demands on the system, for one being an AMO system that needs a lot of certain RF frequencies and digital signaling, combined with microwave electronics and a lot of time-stamped coordination, especially if we want to go to many, many, many qubits. We built a control systems team with FPGA engineers and other specialized engineers to really build our own proprietary hardware that at this point, internally, it's just being designed and built, and we can just integrate it very quickly, and it's sped up our R&D cycle tremendously. So we're very excited about that. So where are we at now? We're actually working together already with a few partners, but we're looking for more ways to engage with everyone. So I also invite everybody to come and talk to me afterwards or tomorrow. We are engaging with people along slightly different ways. For instance, research collaborations. So we're working with academics or people who are in the R&D side for quantum computing applications in larger companies to help them figure out how to leverage some of the advantages of our system for their particular solutions or problems that they're trying to solve. We're also working on optimized algorithm development. So working together with partners to really do algorithm development and figure out how we can leverage this technology to solve some of the bigger problems that we have. I was very excited to see some of the progress that already has happened in this space, and I have no doubt that many more amazing things will happen in the near future. And then, of course, on-premise systems. So we are exploring opportunities with different parties on system sales, essentially building a system and then placing it on site and having the user full control over that system. And those are all the things I wanted to mention. So thank you.
Thank you, Remy. Thank you very much. We have time for some questions. Oh, there is a question here. If you can bring a microphone here.
So you said you are going to use 3D arrays.
Mm-hmm.
So how are you gonna control each individual atom with a laser? Because there will be other atoms in the way, right?
That's a very good question. So I can't give you the exact answer to that question because that's proprietary. But so in a 2D plane, it's easy because you have direct line of sight. And so with the technology that we have, we can actually parallelize some of these operations. So you can do it by row or by column in parallel with individual phase control. So that works in 2D. Once you do it in 3D, it turns out that there are certain tricks you can do where you can make sure that only the qubits that you want to work with are the only ones that see the light that you're sending to them. And so that's how you can scale that up into a three-dimensional system. I know that's a little bit of a roundabout answer, I'm sorry. But
Thank you.
Great. Any other question in the audience? Oh yeah, over there.
Yes, so thank you. So maybe just to attach another question to the previous one. So I assume you're using different atoms, not always the same atoms, same elements.
I can't comment on that.
Okay.
Sorry.
Can you talk about the DARPA effort at all?
Yes, thank you for bringing it up. So we have been awarded a DARPA grant, and so we're working very closely together with DARPA, and we are working together on creating a roadmap to aggressively pursue essentially a path to fault-tolerant computing. And I cannot give you any details about what that roadmap entails, just to say that the collaboration with DARPA has been really fruitful so far, and we're just very excited to be working with them and being part of that program. And, you know, the things that are coming out right now, I think, give all of us a lot of confidence in the path that we're on as a company. Yeah.
So the goal of the DARPA effort is to have what kind of computer by what date?
I can't tell you that.
Well, I thought that was public on the DARPA.
I can't
website.
tell you that because I don't know exactly what the end date is, but what the date is that was promised there, because I just, it is exploring a path towards fault-tolerant computing, so it involves logical qubits. Yeah.
Okay.
A question? I think there was a question here. Yeah, a question here.
So these neutral atom-based, I'm going to say, let's say gates, are relatively slow compared with some of these semiconductor or superconducting qubit switching times. Yeah, how fast is that? How fast do you expect your machine to be?
That's a very good point. So I would say industry-wide, like you're right, our gate times are not going to be as fast as any of the superconducting-based systems. We are faster than the ion-based systems, but that is part of a bottleneck. So part of the technology that we're working on is, as I said, we can parallelize a lot of our operations by working in the rows in the column configuration and some more exotic things that we're exploring. Those give you roughly order of magnitude speed-ups. In the end, what we're excited about is that we do have a path forward on pushing some of these gate rotations to higher and higher speeds. I don't think they will actually get to the superconducting speed limit, but we have some overhead in pushing those to much faster than what they are right now. So that's one path forward. I would also just say that's the issue of wall clock time, where you go like, well, to run a certain circuit at a certain depth takes a certain amount of time. With the coherence times that we have in our qubits, we are not limited by a T2 star coherence effect. So whereas some of the other platforms really need to cram in as many gates as possible before they run out of coherence in the system, in our case, that is not a concern, and it turns into like a wall clock problem that we're just working on. But I think that realistically, it's never going to get to like superconducting qubit speed, but we will make significant improvements over what the current state of the art is.
All right. Well, I think we can. One more question? Okay, my bad.
Yes, thank you. So we were talking about applying these parallel operations to the rows and the columns. Are they fully independent, or they're fully, so there's no restrictions whatsoever?
No, they are all with like individual frequency, amplitude, and phase control. So it's not a global beam thing or anything at all. It's really local control.
Anyone else? Well, if not, let's. Oh yeah, here. It looks like. Anyway, sources by yours.
Presentation is very interesting. We've heard earlier this morning about We've heard earlier this morning about Pascal and its focus on analog mode, at least to start with. And we're going to hear in a moment, I think, about dual mode neutral atom computing. Atom stands out as having focused on a gate model focused approach. Why is that?
That's correct. We're only focused on gates because we believe that the most relevant and value-creating applications will come from gate-based algorithms, and so that's what our sole focus is as a company.